Today we will learn different arrangements of simple vapor compression refrigeration system. The different arrangement with simple refrigeration system are following. Number 1, simple saturation cycle with flash chamber, simple saturation cycle with accumulator, simple saturation cycle with regenerator or heat exchanger, or we can say that the liquid vapor heat exchanger or refrigeration cycle. So first of all, we discuss on simple saturation cycle with flash chamber. So this is the line diagram of simple saturation cycle with flash chamber. First look what are the basic components required for this arrangement. From number 1, we required compressor. Number 2, condenser. Number 3, expansion valve. Number 4, flash chamber. And last one, evaporator. So as compared to the simple vapor compression refrigeration cycle, we required an additional device, that is flash chamber. Why we require this flash chamber? So first of all, we must know about what is flash. As in expansion valve, we know that there is a expansion of refrigerant takes place. Means during expansion pressure drops and slightly evaporation of liquid refrigerant takes place in expansion valve. So at this point 5, just inlet of flash chamber, the refrigerant is available in the liquid plus vapor form. So the vapor formed during this evaporation and expansion valve is called flash. Means the partial evaporation of liquid takes place in. So this is the flash, and this flash plus means vapor plus liquid. So in evaporator, the vapor is of no use. Why so? Because vapor refrigerant absorbs less amount of heat from surrounding as compared to the liquid refrigerant. So at the inlet of evaporator, always try to supply the refrigerant in the form of liquid. So we need a flash chamber for separation of vapor and liquid, and liquid is directly supplied to the evaporator and vapor is directly supplied to the compressor. So this is a simple arrangement. 1 to 2 compressor. In compressor, we know that there is a reversible adiabatic process. This is a pH diagram, pressure specific enthalpy diagram. Reversible adiabatic diagram is isoentropic process. Then in this figure 2 to 4. 2 to 4. 2 to 4 means condensation of superheated refrigerant in vapor form takes place. Means at 2 is the superheated vapor refrigerant which is converted into the saturated liquid refrigerant in the condenser. In 2 to 4 there is a removal of heat. Heat is removed to the surrounding. 2 to 3 is the removal of heat due to superheat, and 3 to 4 removal of heat in the condenser. Means saturated liquid is converted into the saturated vapor is converted into the saturated liquid. At 3 the saturated vapor. Then 4 to 5. Here 4 to 5. In 4 to 5, here is the expansion valve. In expansion valve, there is expansion of liquid refrigerant takes place. During this expansion, from 4 to 5 pressure drops and the refrigerant is available in liquid plus vapor form. Now the fluid refrigerant enters into this flash chamber, we separate out liquid and vapor due to the centrifugal effect. Vapor directly supplied to the inlet of compressor and the liquid is supplied to the evaporator. So 4 to 5 expansion, then 6 to 1. 6 to 1 is the evaporation process, means which extract heat from the surrounding and produce the cooling. And this is the point 1, cycle completes and it repeats in the similar manner. What we concluded, flash chamber is an insulated chamber used to separate liquid and vapor refrigerant by centrifugal effect. It is placed between evaporator and expansion valve. The partial evaporation of liquid takes place in expansion valve. The vapor thus formed is called flash. Vapor absorbs less amount of heat as compared to the liquid refrigerant in the evaporator. So, vapor refrigerant is of no use in the evaporator. So, it is better for flash vapor to bypass the evaporator and directly supply it to the inlet of compression. So by doing this, for same amount of cooling as compared to the simple vapor compression reference cycle, we need less amount of mass of refrigerant for flowing through the evaporator. By doing this, we can reduce the size of evaporator. Hence, cost can be reduced by using this flash chamber. Now, some mathematical calculation to find out the refrigerant effect, coefficient of performance and compressor work and compare it with the refrigerant effect COP and WC of the simple vapor compression refrigeration cycle. Look at this. Let M is the mass of liquid refrigerant supplied to the evaporator. ME. ME is the mass of liquid refrigerant supplied to the evaporator. Then what is MC? MC is the mass of refrigerant just prior to the inlet of flash chamber. MF. The mass of refrigerant which flows directly from flash chamber to the inlet of compression. Now, at the flash chamber, there are 3 points, 1, 5 and 6. Just balance the energy. As we know that flash chamber is an insulated chamber, so there is no interaction of heat between system and surrounding in case of flash chamber. Only balance the heat at the inlet and heat at the outlet of this flash chamber. So, what is the formula? Heat taken by flash chamber is equals to heat given out by the flash chamber. This is simply energy balance. It is a form of energy. So, at inlet, point number 5, and what is the mass of refrigerant? MC. So MC H5 is equals to, at outlet, 6 and 1. This is considered as outlet 1. So MC H5 at inlet, ME, here is the ME, S6 is equals to MF into H1. This is simple equation number 1. Now balance the mass. MC at inlet is equals to ME plus MF. ME plus MF. Now use equation 1 and 2. MC H5 is equals to ME S6. Put the value of MF from this equation into this equation. What is this? Plus MC minus ME into H1. So MC multiplied by H5 is equals to ME into S6 plus MC minus ME into H1. Solve this equation. We get the mass of refrigerant that is supplied to the evaporator at 0.6. ME is equals to MC H1 minus H5 divided by H1 minus H6. So, this is the value of mass of liquid refrigerant supplied to the evaporator. Now, refrigerant effect. What is the refrigerant effect? the amount of heat extracted by the evaporator for cooling. Simply, so heat extracted by the evaporator, from the surrounding, 0.1 and 6, 0.1 and 6, and mass of refrigerant is Me at the inlet of evaporator. So therefore, refrigerant effect equals to Me multiplied by H1 minus H6. Now, put the value of Me from equation 3. Me is equals to MC H1 minus H5 upon H1 minus H6. Put there. The MC H1 minus H5 upon H1 minus H6 into H1 minus H6. H1 minus H6 cancel out. So what is the refrigerant effect? We finally get MC multiplied by H1 minus H5. This is the refrigerant effect in kilojoule. Now, work input to the compressor. Where is the compressor? Compressor is in between 0.1 and 2. Look at this. This is the reciprocating compression. So 1 and 2. The compression between 0.1 and 2. Here mass of refrigerant is MC. MF plus Me. The MF plus Me is equals to MC. The mass of refrigerant at the inlet of compressor is MC. So compressor work is equals to MC multiplied by S2 minus H1 kilojoule. Okay. Now, what is COP? COP is the coefficient of performance, which is equals to desired effect upon required input. What is our desired effect? Cooling, means refrigerant effect upon required input. For this cooling, we required some work is to be done on the compressor, that is WC. Therefore, COP is equals to refrigerant effect upon WC. Put the value of refrigerant effect and WC. Refrigerant effect is equals to MC. Refrigerant effect is equals to MC. Refrigerant effect is equals to MC H1 minus H5, and work input to the compressor is equals to MC S2 minus H1. MC cancel out, and H1 minus H5 upon S2 minus H1. Look at this. H5. 4 to 5 is throttling process, means expansion of fluid takes place.